Today's video is going to talk about valence shell, electron pair repulsion theory. That's quite a mouthful, so most people call it valence shell electron pair repulsion theory. They usually pronounce it VSEPR. So in this theory, what we're really aiming to find is the three-dimensional, if applicable, shape of molecules. And so when you're looking at this theory, the key is first to draw the Lewis structure. So in the previous video, we talked about drawing Lewis structures, and having a correct Lewis structure is really key to then carrying on and figuring out what is the shape of the molecule. So when we're drawing Lewis structures, I just wanted to talk about two different things. There are many very complicated Lewis structures. We're not going to be doing them in this class, but as you move along in chemistry, you'll get more and more complicated molecules. We're going to have in our structures what we're going to refer to as the central atom. And we're going to have what are called terminal atoms. Now, the central atom is what it sounds like. It's the atom in the middle. So if we talk about water, I'm not implying a shape in any way. I'm just drawing its Lewis structure. In this Lewis structure, this would be our central atom. If we looked at another molecule, if we looked at something like a boron trifluoride, boron would be my central atom. So which ones would be the terminal ones? The ones that are attached to it. So my terminal atoms would be because they're on the outside, right? And over here, the fluorines would be the terminal atoms. So when we're applying valence shell electron pair repulsion theory, the first thing is to draw a correct Lewis structure or a plausible Lewis structure, and keep in mind that there's a central atom and a terminal atom. The second step is to determine the steric number, or some people don't like to use this word steric number. Some people call it number of effective electron pairs. Some people call it substituents. It really depends on the author of a textbook. So I like to use steric number and number of effective electron pairs. And so when you're determining the steric number, this is of the central atom. We don't really care about the terminal atoms when we're applying VSEPRs. We're really just looking at the central atom. So if I go back and look at water, and I wanted to find my steric number, I look at how many things are around that central atom. So the steric number is defined as the number of, I'm going to just say things about the central atom. So when we're saying the number of things, what can these things be? Things can be a bond, or some people will say to an atom, right? Or the things could be what are called a lone pair of electrons. And so in water, how many things are around the oxygen? I have a hydrogen, that's 1. I have another hydrogen, that's 2. And then this is a lone pair of electrons. And this is a second lone pair. And so the steric number for water would be 4. sometimes when we're doing this, you might see examples that don't obey the octet rule. For us, all the structures I'm going to ask you to draw should obey the octet rule. There are structures that do not obey the octet rule. So if you're nosing around online and you see things that aren't obeying the octet rule, we're not going there, but that is possible. And so let's try one other one and decide how many, what the steric number is. So if I showed you this molecule, and I asked you, A, what's the central atom? Carbon would be my central atom because it's in the middle of the molecule. How many things are attached to that central atom? Well, I have one thing. This is hydrogen's attached to it, and I have nitrogen attached to it. Notice I don't care that hydrogen's attached by a single bond and nitrogen's attached by a triple bond. The carbon and nitrogen are attached by sharing electrons, and right now it doesn't really matter how many are in there. So the steric number would be equal to 2 for hydrocyanic acid. So this is an important thing that we're going to need to be able to do. Now, what does the theory say? The actual theory states that valence shell, valence shell electron pairs will repel one another. And so if we were looking at something with all single bonds or lone pairs, this is pretty straightforward. So for example, if we looked at methane, this is the Lewis structure. I know I'm writing that quickly, but we're going to practice doing Lewis structures later. And I asked you, A, what is the steric number for this? Again, identify the things attached. We have 4 hydrogens attached, so my steric number is 4. What does that mean? It means this pair of electrons wants to be away from the second pair of electrons, away from the third pair of electrons, away from the fourth pair of electrons. So they're going to spread out as far as possible to minimize electron to electron repulsions. Now, the pair of electrons, these two can't get away from each other. They have to stay together because they're being shared between 2 atoms. But the individual pairs, this pair will want to get away from this pair, away from this pair, and away from that pair. So in a moment, we're going to figure out what shape these are going to be. But I wanted to show you one other thing before we get there. What happens if we go back? Oops, let me get out of green. What happens if we go back to this molecule that I showed you here, and we know that the steric number is equal to 2. Now, if I just said the valence shell electron pair repulsion theory says that the electron pairs want to get away from each other as possible, you might think that this pair of electrons wants to get away from this pair of electrons because we're always going to obey the octet rule. And if you always obey the octet rule, there's always going to be four pairs of electrons, except for hydrogen, right? And so I'm not saying that all the pairs always have to get away from each other. These are part of a bond connecting the carbon to nitrogen. That's why the steric number kind of helps. You can think about this triple bond as one effective electron pair, just for the sake of this theory. Those 3 sets of electrons cannot get far away from each other. Otherwise, how could they be being shared between 2 atoms? They have to be in a common place. So I find the steric number is a little bit more helpful. But the other term that we'll use is this effective electron pair. So you could say the steric number is 2, or we have 2 effective electron pairs. And I'm just giving you different language in case you happen to look at a couple other videos online that you're not confused by this. Okay, so what are the shapes? So to look at the shapes, I'm going to actually try to show you some models. I apologize ahead of time if this is not in focus or great. So what I'm going to do is show you, I'm going to have to go back and forth between sharing the screen and showing you some molecules. But what if you had two? Oh, let me go back. What if we had two, steric number of 2? So you have two things, you want to get them as far away from each other as possible. If this is my central atom, where will two things go to get as far away from each other as possible? They're going to go, right, to the opposite sides, and there's going to be 180 degrees between them. And so we're going to call this linear. If the steric number is 2, the effective electron pairs, whatever they may be, will go on opposite sides of each other, and it will be linear. So how can you get to a steric number of 2 while you're obeying the octet rule? You can have, I'm just going to draw a circle as an atom. So here's my atom. I could have one single bond to another atom and a triple bond to an atom. That's one way to get a steric number of 2. Or I could have a double bond and a double bond. I'm not implying those are oxygens, they're just atoms. And so either way, my steric number is 2. And so in here, I'm attached to two things, 1, 2, 1, 2. Notice the central atom does not have a lone pair. That's because it already has 8 electrons. Remember, 1, 2, 3, 4, 5, 6, 7, 8. Right, and over here, double bond is 4, and if it's got 2 double bonds, it also has 8, so it doesn't have a lone pair. Now, what would those actually look like with molecular models? Well, they would look like this. Let me see if I can get that in focus for you. So here would be a molecule. This is how some model sets make a double bond. Notice there's 2 and 2 here. But what I want you to see is that the atoms, the blue, black, and blue, are all in a straight line, and it's flat, right? The atoms line up perfectly. And so I have a website for you to look at where you can take these and spin them around to kind of get an idea. But here's a linear molecule that involves 2 double bonds. So what does it look like if you have a triple bond? If I had a triple bond, I would be seeing this. Notice I have 3 of these here. Each one is representing 2 electrons, right? And so in here, again, I don't care where these white things are, right? This is just a man-made model set trying to look like the molecule. What I'm really interested in is where are these atoms? And so again, these atoms, if I go black, black, orange, those are all in a straight line. And so this is a linear molecule. They're all in a straight line. So you can have linear in 2 ways. Steric number is 2. I can have a triple bond and a single bond, or I could have 2 double bonds. Either way, I'm going to get a linear molecule out of that. So what happens when the steric number is not 2? What happens when the steric number is 3? Well, now if I have an atom and I have 3 things that want to get as far away from each other as possible, this is kind of geometry, they're going to go out to the quadrants of an equilateral triangle. And so my angle here would be 120 degrees, because if I go all the way around, it's going to make a circle, right? And a circle is 360. So this shape is called trigonal planar. Now, to have trigonal planar and single bonds, you'd have to not obey the octet rule, right? Because if my steric number is 3, that's telling me I can only have 3 things around it. And so there is a molecule, boron trifluoride, that actually breaks the octet rule that people typically show as the sample molecule for this. But what's not good for us in this sample molecule is that it doesn't obey the octet rule. And if you look closely, this has only 6 electrons. Now there's a reason that people draw it that way. You can make it have a double bond and use the right number of electrons, but as you move through Chem 1A, you'll see why that's not the typical way that people draw it. And so how can we get a steric number of 3? Well, the only way we can get a steric number of 3 is if we have a double bond involved. So if we have an atom with a double bond to an atom like this, my bond angles will be approximately 120 degrees still. And this will be trigonal planar. Now planar means that it's flat. We're going to come to something later that's not flat. So that is one shape. I'm going to draw one more thing out for you. So one way we could have a steric number 3 is if we have 2 single bonds and 1 double bond. Again, the 3 things that I'm looking at are 1, 2, 3. This is going to be trigonal planar. Now my electrons, so I'm going to call that my electron geometry, will be trigonal planar, and my molecular shape will also be trigonal planar. But what happens if I have something that looks like this? What happens if I have a steric number of 3? Remember, we're on steric number 3. My 3 things are an atom, and a lone pair. But now what do I have here? I have 1 double bond, 1 single bond, and now I have 1 lone pair. Now this lone pair is tricky because the electrons are still going to go to this trigonal planar geometry. So it's still going to look like this. I'm just going to put my electrons out here kind of in a weird way. I'm just going to show that as electrons, but I'd have an atom here and I'd have an atom here. So my electron geometry is the same as it was over here. It's trigonal planar. But my molecular shape, or some people call this molecular geometry, is going to be different, because when we talk about the shape of the molecule, we only look at where atoms are. And so the atoms are only located here and here. So we don't take into account this lone pair of electrons when we're doing the molecular shape. We do when we're doing the electron geometry, but not for the molecular geometry. So this thing actually has a different shape than it has an electron geometry. And the shape it's called is very technical. It's called bent. Some people will call it V shape. So let me show you what I'm talking about with those two. So if I were to have this molecule, it would look something like this. So here's my double bond. So if you notice, these are going to point out to a triangle. And so I'm going to have right here bond angle going here of 120, bond angle here of 120. So this is my shape trigonal planar. And notice all of the atoms are on the same plane. So that's why it's, don't pay attention to these things. This is just a model kit making the bonds. Where are the atoms? They're all flat. So they're all on the same plane, right? One is not higher than the other. They're all on the same plane. So that is an electron geometry of trigonal planar, and that is a molecular shape or a molecular geometry of trigonal planar. But what happens if one of these atoms is gone? Now, this is just a pair of electrons up here, so I can kind of ignore it. My shape is now going to be bent, or if you turn it this way, kind of looks like a V. So the bond angle here is still going to be approximately 120 degrees, but this will have a different shape because I'm not caring necessarily where these electrons are in my final result of my molecular shape, although I need to know where they are for my electron geometry. Okay, we got one more to go. So the last one I wanted to tell you about is, whoops, sorry. The last one I wanted to show you is if you have a steric number of 4. So there are 3 ways you could have a steric number of 4. You could have something like this, where I have 4 single bonds. Or I could have 3 single bonds. And a lone pair of electrons. Or, like we had water before, we could have 2 single bonds and 2 lone pairs. Now, what will all of these have in common? They'll all have the same electron geometry. What will that electron geometry be? It's going to be called tetrahedral. All of them will be tetrahedral. 4 things trying to get away from each other will always form a tetrahedral. To draw a tetrahedral is a little bit tricky because now this is our first 3-dimensional one. So my atom in the center will be here. And I'm going to use a wedge, and I'm going to use a dash. The bond angle here will be approximately 109 degrees. It's 109.6 if they're all exactly the same. So this wedge means it's coming out of the plane, and this dash means it's going behind the plane. I'm going to show you samples in a minute. I just want to get this all on one slide. What will the molecular geometries be? Well, if there's no lone pairs, the molecular geometry is the same as the electron geometry. If there's lone pairs, the 2 will not be the same. So this one's going to be called trigonal pyramidal. And this one's also going to be bent. So I'm going to show you this with some models. And again, you can go to the website and play around with this, or buy a model kit is also recommended. So let me show you what these look like. So here is a tetrahedron. Notice there's nothing I could do to get all the atoms in the same plane. They're not all in the same plane. So when we draw this, usually on a piece of paper, what we try to do is get 3 atoms in the same plane. And so in this case, if I tried to make this atom, the 2 that my fingers are on, and this one in the same plane, what's true is this guy's pointing out at us and this guy's going back behind. So this would be the wedge and this would be the dash. And so that would be a tetrahedron. Notice it's very symmetric. It doesn't matter which corner I pick, they're all evenly spaced, right? So that's a tetrahedral. 4 single bonds. Now, what if there's 3 single bonds and a lone pair? Well, it's going to be almost exactly the same, except for the top corner is going to be missing. And so now it's going to look like the bottom part of this molecule, but we're not going to take that top corner. So if this thing is called a tetrahedral, this cannot be called a tetrahedral, but this is not flat. Notice that the black atom is higher up than the orange atoms. And so this is not trigonal, although from this side, it looks like it's trigonal planar. It's not trigonal planar. Trigonal planar would be like this, everybody on the same plane, right? Everybody, only 3 things here, and I could make that so, whoops, you could see that it's perfectly flat. This is not flat. This is called trigonal pyramidal. And what happens if I go to the next extreme and 2 of them are lone pairs? Well, if 2 of them are lone pairs, these are both gone. And now what shape do I have? I have a piece of this, right? Which is really a piece of this, right? And so this one is missing, this has all the corners, tetrahedral. Missing 1 corner, trigonal pyramidal. Missing 2 corners, bent. This bent is a little bit different though, because this bent has a bond angle of 109, whereas this bent with the double bond situation, this had a bond angle of 120. So those are the shapes that you need to know. And if you look at the lab for this week, you look at the lab for this week, you will see a nice diagram of all of these shapes. So the summary is found in lab number 6. And so you'll see a nice table that goes through all this, and we'll go through it in lab this week.